Okay, good morning, everyone. I'm Wen-Tau Yih from Microsoft Research. Today, instead of talking about my own paper, which is going to be presented on Tuesday, I'm going to talk about my colleagues' deep neural network model for measuring semantic similarity and its application to modeling interestingness. This is joint work of Jianfeng, Patrick Pantel, Michael Gamon, Xiaodong, Deng, and Shen, all from Microsoft Research. So computing semantic similarity is a fundamental component that can be seen in almost all NLP applications. For example, in machine translation, given a bunch of sentences in different languages, what we want to know is what we need to do is to judge whether they have the same meaning. And in web search, in order to fulfill users' information need, we will need to measure the semantic relevance between the queries and documents. However, existing solutions to these problems are often unsatisfactory. For example, language discrepancy, where a concept can be expressed using different vocabularies and in different language styles, usually cannot be handled well by lexical matching. And word embedding and topic models, which they are typically trained in an unsupervised way and are often not optimal for the task of interest. So in this work, we propose a deep semantic similarity model for measuring semantic similarity. The model actually maps text to real value vectors in a common latent semantic space that is language independent. Once the objects are mapped to these vectors, the semantic similarity of these two objects are going to be measured using some distance function, such as cosine in this space. And the mapping of the vectors is actually performed via deep neural network models that are optimized using a task-specific objective. So this model already has several successful cases and produces state-of-the-art results in many NLP applications, such as in web search, machine translation, and question answering. And in this work, we're going to show how we can adapt this model to modeling interestness for recommendation. Essentially, what we want to know is what interests a user when she is reading a document. So in the remaining of my talk, first I'm going to give you some more description on the task of modeling interestingness, including automatic highlighting and contextual entity search. Then I will give you more detail on the model on this model, deep semantic similarity model, followed by the experimental results and some conclusion and discussion. So we identified two tasks of modeling interestingness. The first one is called the automatic highlighting. Given a document, we want to highlight the key phrase that represent the entities in this document, such as person, location, organization, and that interests the user when she is reading this document. Obviously, document semantics influences what is perceived as interesting to the user. For example, if the article is about the movie, then we may assume that the user is going to be interested in knowing the actor or the characters in this movie. The second task is called contextual entity search. Given those highlighted key phrases, we would like to recommend new interesting documents by searching the web for supplemental information about these entities. And in this case, a key phrase, or typically people call it mention, may refer to different entities. So obviously, we need to use the contextual information to disambiguate. So let me give you an example. So suppose a user is reading a document about Einstein's theory of relativity. And so we want the system to automatically suggest some key phrases, such as the words underline words over here. And then user may click one of them to get more information about this phrase. In this case, we will hope to find the more information about this entity. However, since the term ray of light can mean different things, such as one of the popular songs from Madonna. So in this case, if we actually just do keyword matching and then use the most frequent choice, then it's easy that we'll get some error here. So instead of doing that, we would like to use the contextual information, essentially the document or the some words surrounding this key phrase to help us to decide which one is the correct entity. In this case, there would be the rate of light thought experiments of Einstein. Okay, so how do we apply DSSM in this particular task to measure semantic similarity? So for the first task, automatic highlighting, what we want to do is really just to measure the semantic similarity between the context, which is the document over here, and also the potential key phrases that we may want to highlight. And for the second task, the contextual entity search, so we want to compare two things. On one side is the key phrase and also the context. And on the other side is the entity and its corresponding page. For example, some Wikipedia page about this entity. Now, let me talk about let me give you more detail about this model, this deep semantic similarity model, DSSM. So DSSM is a Siamese neural network model. The input is two sequences of words that represent the text objects X and Y that we want to compare. And as I mentioned earlier, in the end, the model will actually map these two sequences into some low-dimensional vectors in the latent space. And to measure the semantic similarity of these two objects, X and Y, essentially we want to use the cosine similarity of the corresponding vectors over here. And the learning process essentially is trying to maximize the similarity between the object X and the object Y if they are labeled as positive pairs. So this model, the DSSM, actually consists of two deep neural network structures, one for each text object. And these two networks actually share similar model forms, but the model parameters are, of course, different. So there are two unique properties of this DSSM network design. The first one is called the word hashing layer. So instead of using the word sequence directly, we'll use the word hashing function to map this word sequence to some sequence of sub-word units, such as letter n-gram. And the second property is the convolutional mixed Poolean layers. So we use that to handle variable length of the input and also try to identify the keywords and concepts in these input objects X and Y. So let me give you more detail about these two things. The first one is the word hashing function. So the original motivation of using a word hashing function is actually to control the dimensionality of the input space. In this particular case, we use the later trigram representation. So you will actually break each word into a sequence of 3 letters, such as cat becomes these 3 letter trigrams. And by doing that, we can control the dimensionality of the input space to roughly 50,000 in English. And also it helps eliminate the annoying auto vocabulary issues. And this design also has some additional benefits. For example, it can help capture some sub-word semantics, such as the morphological variations of words. And also words with small typos have similar row representations. So one concern you may have is, because we actually introduced the hashing function, so what about the collision problems? Essentially, what we mean here is that maybe different words could be mapped to some sequence that have the same later trigon representation. Fortunately, an empirical study conducted using a large corpus suggests that usually the collision rate is actually fairly low. Okay. So the convolutional layer works as follows. So essentially, we want for each subsequence of the input features, we would like to project them to some kind of topic vectors. So in this case, W1, W2, W3 will be mapped to this U2 vector, where topic 1 is the prominent topic. And here, U3 is projected from W2, W3, and W4. And the fourth, the topic 4 is the prominent one. Okay. So remember that the input actually is a variable length of word sequence. So we would like to, we will need to use a max pooling operator to map these local vectors to a global vector. Conceptually, the global vector captures the important topics of the whole text. So the process is actually pretty straightforward. For each dimension, you just look at all the local vectors. For example, for dimension 1, you actually just check all the dimension 1 of each local vector and use the largest one as its value, such as this case. Okay, and then so in this process, because we can trace where the original values come from, so you can also find the representative keywords for those topics. Okay. So this estimate is learned using examples of labeled pairs. So consider a document X and with two key phrases, Y plus and Y minus. And let's assume that Y plus is more interesting than Y minus to a user when reading document X. And remember that we use cosine similarity of the corresponding vectors of X, Y in the semantic space to measure similarity. And those vectors are mapped by the whole model parameterized by theta. So theta is actually the model weight. So we define delta as the difference of the similarity of the positive pair and negative pair. With the goal to maximize data, we use the localness function over here. And the optimization actually uses this standard mini-batch stochastic gradient descent with GPU support. Now, let me give you some result of the experiments. Okay. So we use the web browsing logs to extract label pairs for these tasks. For example, in the task of for automatic highlighting, when reading a page P, a user may click a hyperlink H. So the click information is treated as the implicit signal that the user feel the hypertext of H is actually interesting given this document. So in this case, for the task of automatic highlighting, we just use the pairs of the text in P, which is the page, and also the anchor text of H to form the positive label pair. And then for the contextual entity search task, we can just use the hyperlink H. For example, if a hyperlink H points to a Wikipedia page P', and then we know that this mention is actually means this particular bush, the rock band. So in this case, we'll form the pairs by using the anchor text of H and the surrounding words of H. And the other side will be the words in the Wikipedia page P'. Okay. So for automatic setting, for automatic highlighting the setting, we actually use a kind of simulation to evaluate this task. So the idea is as follows. So we use a set of anchor text as the candidate key phrases to be highlighted. And we collect a number of user clicks from the logs and then use that to form the gold standard rank of key phrases. And when evaluating a model, we just ask the model to rank or pick the top K keywords of the candidates. And the final evaluation is just the standard evaluation for ranking, the NDCG score. In terms of data, we have 18 million occurrences of user clicks from a Wikipedia page to another, which are collected from 1 year web browsing logs. And we use 60% of the data as for training and 20% for validation, and the remaining 20% for evaluation. So first, let's look at some baselines here. Random is just a random baseline, which is pretty low, and this suggests that this task is actually not trivial. And the basic feature here is a classifier we actually built using the Boost decision tree learner with some standard document features such as anchor precision, frequency of anchors, and anchor density, and so on. And no sophisticated semantic related features are used in this classifier. And we compare the 3 different kind of semantic related models by adding them as additional features to the basic classifier. So the first one is a topic model that is here, the LDA vector, is from the previous work of one of the a couple of co-authors of this paper, which is the previous state of art. You can see that after adding some semantic features, we can see that it already improved a lot. And in some cases, we may have some specific semantic features provided by humans. In this case, if we only consider pages from Wikipedia, then we can use the Wikipedia categories as additional features. And this actually shows that we can have quite a lot boost compared to previous models. However, keep in mind that these kind of features are not general and then do not exist for general documents. And finally, we can see that the DSSM vectors, when used as features, is actually pretty effective and perform the best. Okay. So for the second task, contextual entity search, so we use the same training validation data as in the automatic highlighting experiments. And for evaluation, we sample 10,000 web documents as the source document. And we use the entities detected in those documents as query, and return up to 100 returned documents as the target documents when we issue those queries to Bing. And we then have human annotators manually label which documents are good pages describing the entities. In the end, we have roughly 870,000 label pairs in total. The evaluation metrics we use are NDCG and the area under the ROC curve. So again, the baseline performance, BM25, which is a classical document models in information retrieval, doesn't perform very good in this task. And BLTM is a bilingual topical model we proposed previously, which is a strong baseline over here. And we compared 2 variations of DSSM here. DSSM bag of words essentially is a simplified DSSM model without convolutional layer and maximum pruning structure. And as you can see, it's already pretty strong and then has a significant boost compared to other baseline models. And again, the full DSSM model actually is still the best and outperforms all other models here. So in conclusions, in this talk, I introduced the task of modeling interestingness for recommendation. Essentially want to answer the question that what interests a user when she's reading the document. And we proposed the deep semantic similarity model for this task. It maps text to feature vectors in the latent semantic space. And the mapping is done via a deep neural network structure that are optimized using a task-specific objective. And we got basic result in modeling interestingness and also got pretty good performance in other tasks we have tried. In the future, we will keep improving this model by incorporating more structured information, and we are also trying to apply this model to more applications. And this ends my talk. Thank you.
So we have time for a couple of questions.
Yeah, thank you. I'm curious what the intuition is of replacing the words with letter trigrams. It seems like that would lose some information, although if you have a sequence of letter trigrams, you probably retain it. But the bag of words with letter trigrams seem to work almost as well as the words. You showed a...
You mean this one?
That looks like a bag of words of three-letter letter trigrams almost did as well as the full sequence. Can you talk about the intuition why that would be so? It seems counterintuitive.
Yeah, so, well, first of all, I have to emphasize that I'm actually not the one of the co-authors. So I'm not particularly sure whether here bag of words is really bag of words or bag of letter trigrams. But let me answer your first question first. So the original motivation is actually to control the dimensionality of the input space. So because the first layer is actually a big projection matrix. So it's kind of like you have a vector in the original high dimensional space, and you want to map it to a low dimensional space. So when you have a lot of parameters if you actually don't have a large dimension in the input space. So really, original motivation, as far as I know, is to control that dimensionality. And then for that, the word hashing is actually some kind of method that you don't really like to do. As you say, you may actually disrupt or actually make the things faster. But they try different solution and then conclude that later trigram actually is the basic compromise in this task. If I remember it correctly, when they did this design, when they test this in, I think the first set of experiments is on web search. Initially, the learning curve actually drops, which means it actually made the performance worse than if you just use words directly. But because of this design, they are able to actually use a lot of data. So eventually, actually, it improves the model that performs better.
A very good talk. Thank you. Just quick question. Do you have any intuition behind the design of the layer of the neural network? I saw you have several layers. Do you have any intuition under that? And the second question is, I saw a lot of improvement from neural network using the unsupervised initialization. So do you apply any initialization for that? And the third question is, did you compare with some symbol based on some similar machine learning algorithm like SVM or MaxN or whatever?
So the first question is about the intuition of the design of different layers. This model, in my opinion, is not particularly very deep, right? So, so I actually described two different layers, like the word hashing part and also the convolutional part. Actually, that's really the main layers of design over here. And your second question is about the initialization and also compared to other baseline. I believe the baselines we compare are pretty strong over here, and I'm not particularly sure about whether they have tried different ways to initialize the parameters. But personally, I got inconclusive lessons when trying different things. So it may help, it may not help. Yeah.
I'm sorry.